Today we're going to talk about something you use every single second you're online. It's a piece of 40-year-old technology, the invisible engine of the internet, a system that, by all rights, should have failed decades ago, but somehow it's still holding our entire digital world together. This is the wild story of IPv4.
All right, let's just pause and think about this because it's a genuinely baffling question. We've got billions of people online and tens of billions of devices. Your phone, your laptop, your smartwatch, even your fridge. So how on earth can a system with fewer unique addresses than there are people on the planet possibly manage all of that traffic? That's the mystery we're going to solve.
So to get our heads around this, we have to start with the absolute foundation of how the internet works, the digital address. Every single device, without exception, needs one of these to send and receive information. You can think of it just like a postal address, but for bits of data.
And this number you see here, that's it. That is the grand total. The entire number of addresses available in the original system, Internet Protocol version 4, just under 4.3 billion. Now back in the 1980s, that must have seemed like a nearly infinite number. Today, it seems impossibly small for a network that spans the entire globe.
So why that very specific number? Well, it all comes down to the original design. An IPv4 address is what's called a 32-bit number. And if you do the math, 2 to the power of 32 gives you exactly that 4.3 billion unique combinations. That 32-bit limit is the source of our whole story. It created a finite universe of digital real estate.
But, having a limited number of addresses wasn't even the biggest problem at first. The real issue, the thing that almost brought the whole system crashing down, was how those addresses were given out. The original system was incredibly rigid and, as we're about to see, just unbelievably wasteful. This system was called classful addressing, and what it did was chop up all 4.3 billion addresses into a few fixed sizes. So huge organizations like IBM or MIT, they got a Class A block, which came with over 16 million addresses in one go. But a small organization would get a Class C block with just 256. There was really nothing in between. It was like the post office only sold P.O. boxes in two sizes, a whole state's worth or a single box. It was completely inflexible. And this wasn't some secret. People knew this was a huge problem right from the start. This quote here, from some of the early documentation, just nails it. An organization might only need, say, 50,000 addresses, but they'd be forced to take 16 million, meaning millions and millions of addresses were just sitting there, completely unused. This waste was literally baked into the internet's DNA. Okay, so let's recap. You've got a limited supply, and you're giving it away in these huge, inefficient chunks. What do you think happens when the internet suddenly explodes in popularity? Yeah, you get a crisis. You start running out of road, and you're running out of it fast. And just look at how quickly this all unfolded. IPv4 becomes the standard in 1981, but by the early 90s, with the World Wide Web just starting to take off, engineers are already sounding the alarm bells. They could see the cliff edge from miles away. And sure enough, by 2011, it officially happened. The central pool of IPv4 addresses ran dry. The internet was, for all intents and purposes, full. So why didn't everything just grind to a halt in 2011? How are we all still here? Because for years, brilliant engineers had been developing a series of incredibly clever solutions. And you can think of these less as boring technical patches and more as the heroes of our story, the hacks that saved the day.
These three technologies are pretty much the reason we're all still online today using IPv4, subnetting, NAT, and CIDR. Each one is an ingenious workaround that stretched the life of this old system far, far beyond what anyone ever thought possible. Let's break them down real quick.
First up, subnetting. So remember that company that got 16 million addresses? Subnetting is like them saying, okay, we're not going to ask for more addresses from the outside world. We're just going to cleverly divide up the giant block we already have. They create smaller internal subnetworks for different departments or buildings, all while looking like one single entity to the rest of the internet. It's a classic divide and conquer strategy. Next is NAT, Network Address Translation. And this is the magic trick you use every single day. Your home router does this. It gives all your devices, your laptop, your phone, your TV, their own private addresses that the internet can't even see. Then, when one of those devices wants to connect to the outside world, your router lets it share your one single public IP address. It keeps track of who's talking to who by using these unique port numbers you see here. Honestly, NAT is probably the single biggest reason the internet didn't just collapse years ago. And our third hero is CIDR, or classless addressing. This is the hack that went right back and fixed that original wasteful class A, B, C system. With CIDR, the whole rigid rulebook was just thrown out the window. Now, an internet provider could give a company exactly the number of addresses it needed, not 16 million, not 256, but a custom-sized block. This flexibility slammed the brakes on waste and made the remaining address pool last much, much longer.
Okay, so those hacks are amazing at managing the addresses. But how does a piece of your data actually use those addresses to get where it's going? For that, we have to look inside the digital postcard of the internet, the IP data packet.
At the very front of every single packet of data is something called a header. Think of it like the writing on the front of an envelope. And the core parts are actually pretty simple. You've got the source and destination addresses, which is just the from and to. Then there's this really clever thing called time to live, which is basically a self-destruct timer, so lost packets don't just bounce around the internet forever. In a protocol field that tells the computer what to do with the data when it arrives, like, hey, this is for a web browser, or this is for an email client.
But here is the absolutely wild part about IPv4. It's what's called a best effort protocol. That means it doesn't actually guarantee your data will ever get there. Seriously, if a router somewhere along the path is too busy, or if there's one tiny error in the header, poof, the packet is just dropped, thrown away. It was designed for speed, not reliability, and it relies on higher-level protocols like TCP to do the hard work of making sure the whole message actually arrives in one piece.
So, these clever hacks have kept the internet running for decades longer than they ever should have. But they are still, at the end of the day, just hacks. They're brilliant band-aids. So for the final part of our story, let's take a look at what the permanent solution looks like.
Take a look at this number. It's 340 undecillion. I mean, it's just a completely incomprehensible number. That is the number of addresses available in the successor to IPv4, which is called IPv6. It's a number so vast that we could assign a unique address to every single atom on the surface of the Earth and still have addresses to spare. The problem of running out has been solved, permanently. So what's the big takeaway here? IPv4 is this amazing 40-year-old system kept alive by decades of pure engineering brilliance. And its replacement, IPv6, is already here, offering a virtually infinite number of addresses. The thing is, the transition is slow, it's complex, and it's expensive, which leaves us with a final thought. The internet we have today is a true marvel of ingenuity, but its future really depends on us finally letting go of its past.